Okay, so this video is meant to go through the idea of capacitors and understand how they work and how they can store energy. So a capacitor is essentially a device that stores energy via an electric field. So it stores electric potential energy. Via an electric field. And a capacitor is essentially charged by removing charges from one conductor and placing them on a second conductor, so there is an electric field between two conductors. I'm going to model this out. Second conductor and creating an electric field between the two. So the easiest way to model this out is with what's called a parallel plate capacitor. And I'll show it to you kind of like visually on the board, and then when we get back in class, I will actually model it out and show you an actual capacitor and kind of how they get this really large surface area into this really small space. Okay, so essentially what it is it's exactly what it says it is. It's a parallel plate, so you have basically one conducting plate and a second conducting plate, and you connect these to some sort of power supply, some sort of charge device. So here's my battery. And then I've got one side connected here to positive, the other side here connected to negative. And what happens is that if you connect one side to negative, if you provide a path for the electrons to leave the power supply, they will do so in a heartbeat. So you get all these negative charges, and they're like, getting out of here. And you get this buildup of negative charges on this plate here. And the amount of charges that can build up on this plate depend on a couple factors, like, what is that plate? How big is that plate? And if you have a whole bunch of negatives on this side, then by induction, because remember, everything starts off neutral, right? So this plate is neutral. So it's got positives and negative charges. But if you have a whole bunch of negatives on this plate, the negatives on this plate say, hey, I don't want to be near those negatives. And so through the process of induction, the negatives on this plate, they leave. And they're like, I'm okay. I can go to this positive source here. I'm attracted to that. And what you end up having is like a deficit of negatives on this plate. And so naturally, this side will be more positively charged and this side will be more negatively charged. And so you have a negative plate and a positive plate, and if you leave it connected to the power supply, you will end up having the same voltage difference in these two plates as you do with the power supply. So if this is a 9-volt battery, you will eventually cause enough charge separation to occur that there will be an electric potential difference of 9 volts between those two plates. Okay? So this is effectively what a capacitor does. It takes whatever the voltage of the power supply you're connecting it to, and it provides that voltage difference between the two plates on the capacitor. Okay? So let's talk about what are the physical limiting factors, because we said, well, this is how many volts, the amount of volts you can supply it with depends on what you connect it to. But there is a certain limiting factor in terms of well, what's the capacity of the capacitor, and that's called capacitance. I know, novel concept, okay? So capacitance is basically the amount of charge. I wouldn't say it's amount of charge. It is basically, what's a better way to describe it? It's an indication of how much charge the capacitor could hold. So if it's a really big capacitance, it can hold lots of charges, and if it's a really small capacitor, it can't hold many charges. I have way more room here than I allotted for. The symbol for this is a capital C. The equation for this is capacitance is equal to epsilon times A over D. Epsilon is equal to the permittivity of the space in between the plates. If it's just air, then air has a value of what's called epsilon naught, and that is equal to 8.85 times 10 to the negative 12. And I don't remember. It's got some units, but I don't remember the units offhand. I'm guessing it's farads per meter? Not important. You can put other things in between it. There are certain types of materials that you can put in there which allow you to store more. Because think about this. If I have all these charges and I put a whole lot of negative charges here, it's like lightning. If I have too many, there's going to be such a strong attraction over here, they're going to leak off, right? But if I put something in here, in this space, I can prevent the charges from leaking off, and I can hold even more charges. And that material that you put in there is a material called a dielectric. And so if you put a material in there that has a larger dielectric value, then you could have a larger capacitance in your capacitor. For our purposes, we are going to work with air-filled capacitors, and so this is the epsilon value that we would work with, okay? Let me come back here with my equation. A is the area of a plate. So it's just like one side. It's not like twice the area. And it is the limiting area. So if for some random reason one of your plates is smaller than the other, then it would be the size of the smaller plate. And then D is the distance between the plates. And you have to have common units. And so if your area is in, well, if your area, it needs to be in meters. Okay? So make sure you convert that properly. The units for capacitance are called farads. They are named after Michael Faraday. It's a symbol of capital F. But a farad is really, really, really big. And so oftentimes we work with units of microfarads. Microfarads is like the industry standard if you are looking at labeling capacitors. But I suppose you could also do like nanofarads or millifarads. But if you were like to go and buy a capacitor on the street, it would be in terms of microfarads, okay? So the capacitance tells us how much charge we can store on the capacitor. That then can lead us to, like, quantifiably, how do I know how much charge we can store? Okay, so the amount of charge on a capacitor. The amount of charge on a capacitor depends on, well, what's the capacity, right? Like, how big is my space? But then also, how big is my power supply, right? Like, if I have a really tiny power supply that doesn't have a lot of charges like innately with it or a low voltage value, then I'm not going to be able to put a lot of charges on there. And so the charge on a capacitor, we're going to do this as big Q instead of little q because it's quantity of charge, like it's a huge amount of charge we're looking at, not just a single point charge. Q is equal to capacitance times the potential difference, okay? So this is the capacitance of the capacitor. And this is the potential difference the capacitor is connected to. So the amount of charge I can store on the capacitor innately depends on what's the capacitance of my capacitor and then what is the voltage that I am connecting it to. So now that we can figure, like, quantify how much charge I can put on here, then I can think about how much energy can this thing store, right? So if I think about the energy stored in a capacitor, if I think about electric potential energy, remember electric potential energy was equal to QV, right? And this was if I had a set voltage in a region and I had a Q at that point, what was the amount of potential energy in my system? With a capacitor, because we're having charges on this plate and this plate, we're looking at the average, so it's 1/2 QV. So this is the charge on my capacitor times the voltage on that capacitor. But remember, Q can also equal to CV. So there's a couple variations of this equation that we can see. We can see that U would equal, if instead of having Q, I put CV, this would become 1/2 CV squared. And another variation I could have of this is if instead of having voltage here, I could rearrange this to say that Q over C is equal to my voltage, right? So this would be equal to 1/2, instead of V, I would say Q squared over C. So there's just different iterations or variations you could have to determine the electric potential energy if you know either two of the three things. If you know the charge, if you know the capacitance, or you know the voltage, you should be able to figure out the amount of energy in our capacitor, okay? So when we get back into class, we'll talk about like if the point of a capacitor is to store energy, how do you access that energy? And when we get back to class, we will talk about how do you access that energy.